Welcome to Astronomy Daily. I'm your host, Anna. On today's cosmic journey, we're exploring some truly mind-bending developments in the world of space and astronomy. The universe has thrown scientists a major curveball with new findings, suggesting our understanding of dark energy might be completely wrong. We'll also look at the ongoing saga of Boeing's troubled Starliner spacecraft and China's ambitious plans to enter the crewed spaceflight arena. Plus, we've got fascinating discoveries to share. From an exoplanet so strangely light that scientists can't figure out what it's made of, to dramatic evidence of a white dwarf star actually devouring one of its planets. And we'll explore new research suggesting that the beautiful feathery structures seen in spiral galaxies might form through surprisingly simple physics. So buckle up for a tour of the latest breakthroughs and mysteries from the cosmos as we journey together through the wonders of our universe. And this first story is a real mind-bender. The universe just might be weirder than we thought. Astronomers studying the largest ever map of the cosmos have uncovered evidence that could dramatically shake our fundamental understanding of how the universe works. Using the Dark Energy Spectroscopic Instrument, known as DSI, scientists have analyzed nearly 15 million galaxies and quasars, spanning an incredible 11 billion years of cosmic time. And what they found suggests we might have gotten dark energy completely wrong. Dark energy, that mysterious force believed to be driving the accelerating expansion of our universe, has long been thought to be constant. But this new analysis hints at something far more complex. Dark energy may actually be evolving over time. This isn't just a minor adjustment to our models, it's potentially a complete rewrite of the prevailing lambda CDM model of cosmology that scientists have relied on for decades. The findings came from combining DESI's observations with other critical data, including information from star explosions, the cosmic microwave background, and weak gravitational lensing. Together, these diverse observations point to the same surprising conclusion. The fundamental force we thought was constant throughout cosmic history appears to be changing. David Schlegel, a DESI project scientist at the Lawrence Berkeley National Laboratory, put it plainly. It's true that the DSI results alone are consistent with the simplest explanation for dark energy, which would be an unchanging cosmological constant. But we can't ignore other data that extend to both the earlier and later universe. Combining DESI's results with those other data is when it gets truly weird, and it appears that this dark energy must be dynamic, meaning that it changes with time. This realization puts science at a remarkable crossroads. Dark energy and dark matter together make up approximately 95% of our universe, yet they remain largely mysterious as they don't interact with light and can't be detected directly. If dark energy is indeed changing over time, it would force us to completely rethink the lambda CDM model that maps the growth of the cosmos and predicts its ultimate fate. As astrophysicist Catherine Hamans from the University of Edinburgh noted, it's kind of exciting that the universe has thrown us a curveball here. The existing theories simply don't align with what we're now observing. The numbers don't add up, and scientists are facing the thrilling and terrifying prospect of having to develop new physics to explain what's happening. What makes this finding particularly compelling is that it pushes the observation's disagreement with the standard model to the very edge of what physicists consider a significant discovery. With more data collection underway, we may soon cross that threshold and enter a new era of cosmological understanding. If dark energy is indeed evolving, we're looking at a fundamental shift in our understanding of the universe. This isn't just an academic concern. It has profound implications for the ultimate fate of everything we know. For decades, cosmologists have built their models on the assumption that dark energy remains constant throughout cosmic time, exerting a steady outward pressure that counteracts gravity's inward pull. What's particularly striking about DSI's findings is how they transform when combined with other cosmic observations. While DSI's data alone shows only a weak tension with the standard lambda CDM model, adding information from the cosmic microwave background, supernovas, and gravitational lensing pushes this discrepancy to near-discovery levels. The statistical significance approaches what physicists call a 5 sigma result, the gold standard for declaring a new discovery in physics. According to Schlegel, these combined observations suggest that either dark energy is becoming less important today, or it was more important early in the universe. Either scenario would dramatically alter our understanding of cosmic evolution. If dark energy weakens over time, the universe's expansion might eventually slow, potentially even reversing into a big crunch. Conversely, if dark energy strengthened in the past and maintains its current level, we could be headed for an accelerated expansion that tears apart galaxies, stars, and eventually atoms themselves, the so-called Big Rip scenario. This discovery challenges Einstein's cosmological constant, represented by lambda in the lambda CDM model. Einstein originally introduced this constant as a mathematical fudge factor to create a static universe, later calling it his greatest blunder when the expanding universe was discovered. Ironically, dark energy later revived this concept, but now even this updated version appears insufficient. Adam Rees, who won the 2011 Nobel Prize in Physics for discovering dark energy's accelerating effect, considers this potentially the biggest hint we have about the nature of dark energy in the 25 years since we discovered it. As he explains, if confirmed, it literally says dark energy is not what most everyone thought, a static source of energy, but perhaps something even more exotic. Fortunately, a fleet of new experiments is joining the investigation. The Euclid Space Telescope, NASA's Nancy Grace Roman Space Telescope, and DESI itself, which will eventually measure 50 million galaxies and quasars, will provide unprecedented data to confirm or refute these findings. These observations will help determine whether we're truly witnessing the beginning of a cosmological revolution. What makes this scientific moment so exciting is its profound uncertainty. We stand at the threshold of potentially rewriting our understanding of the universe's basic operating principles. Dark energy may be losing strength as the universe ages, or it might have played a more significant role in the early universe than previously thought. Either way, the implications ripple through every aspect of cosmology, from the birth of the first stars to the ultimate destiny of all cosmic structures. Next up in today's news, Boeing's troubled Starliner spacecraft is facing yet another setback, with NASA officials now considering whether a third uncrewed test flight will be necessary before the vehicle can carry astronauts again. This comes after what was supposed to be an 8-day test mission turned into a 9-month ordeal for astronauts Butch Wilmore and Suni Williams. The two NASA astronauts finally returned to Earth this week, but not on the Boeing spacecraft that took them to the International Space Station. Instead, they splashed down in a SpaceX Dragon capsule, a vivid illustration of how Boeing's technical problems have forced NASA to rely on its competitor. We're looking at some options for Starliner, should we need to, of flying it uncrewed, Steve Stitch, chief of NASA's Commercial Crew Program, told reporters. The space agency wants to validate that Starliner's thrusters can perform as designed in the unforgiving environment of space, something impossible to fully simulate in ground tests. The issues with Starliner's first crewed mission emerged shortly after launch, when the spacecraft suffered 5 thruster failures and experienced concerning leaks of helium, which is used to pressurize the propulsion system. These problems were serious enough that NASA determined it would be too risky for Wilmore and Williams to return on the spacecraft, leaving it to fly back to Earth empty while the astronauts remained on the station. For Boeing, this represents not just a technical challenge, but a competitive disadvantage. While Starliner has struggled through its development process, SpaceX's Crew Dragon has already flown 11 astronaut missions for NASA, establishing itself as the reliable workhorse of America's human spaceflight program. The financial implications for Boeing are significant as well. The aerospace giant has already absorbed more than $2 billion in charges related to Starliner development since 2016, the ceiling of Boeing's fixed-price $4.2 billion. NASA contract has grown by $326 million since being awarded in 2014, with the company having received roughly half that amount during development. This stands in stark contrast to SpaceX, which has not only successfully delivered on its initial contract, but has secured additional missions due to Starliner's delays. The value of SpaceX's initial $3 billion NASA contract has grown to nearly $5 billion, largely because NASA has had to book extra Dragon flights while waiting for Starliner to become operational. Boeing plans a ground test this summer focusing on propulsion system components, aimed at validating potential fixes. But the timeline for Starliner's next flight, crewed or uncrewed, remains uncertain, as NASA and Boeing engineers work through the complex technical challenges that have plagued the spacecraft's development. The technical issues plaguing Starliner represent yet another costly setback for Boeing in what has become an increasingly challenging development program. The aerospace giant has already invested more than $2 billion of its own money into the spacecraft, trying to create a viable competitor to SpaceX's Crew Dragon. NASA officials are now carefully weighing their options, with Steve Stitch emphasizing that a key purpose of an additional uncrewed test would be to verify that Starliner's thrusters can perform properly in the vacuum of space. This propulsion system has proven particularly troublesome, with the thruster failures and helium leaks during the first crewed mission highlighting problems that couldn't be adequately identified during ground testing. Boeing's financial commitment to Starliner keeps growing beyond initial projections. The ceiling of their fixed-price NASA contract has expanded by $326 million since being awarded a decade ago, reaching $4.2 billion total. Yet the company has only received about half that amount so far during the development phase, with certification for routine flights still elusive. Meanwhile, Boeing isn't just looking at Starliner as a NASA taxi service. The company has broader commercial aspirations to use the spacecraft for transporting customers to and from privately built space stations currently in early development. This represents the kind of non-government revenue stream that SpaceX has already started capturing with its fully private Dragon missions. But Starliner's uncertain future complicates these commercial ambitions. A NASA Safety Advisory Panel noted in January that while significant progress was being made in post-flight technical investigations, the propulsion system issues remain unresolved. Until Boeing can definitively fix these problems, Starliner's path to certification and commercial viability remains blocked. The contrast with SpaceX grows starker with each passing year. While Starliner has yet to complete a fully successful crewed mission, Crew Dragon has become the workhorse of America's human spaceflight program with 11 successful astronaut missions already completed. This operational track record gives SpaceX a tremendous advantage in both government and private markets. For Boeing, the stakes go beyond just this spacecraft program. The company's reputation as a premier aerospace manufacturer has already faced challenges with its commercial airline issues. Starliner was meant to showcase Boeing's capabilities in the growing commercial space sector, but instead the ongoing difficulties have highlighted the company's struggles to deliver complex space systems on budget and on schedule. Meanwhile, China's space industry seems to be going from strength to strength. In a bold move that signals a new era for China's space ambitions, a commercial space company called Beijing Ziwei Yutong Technology, better known as AZ Space, has announced plans to conduct orbital crewed flight tests by 2027 or 2028. This represents a significant milestone for China's commercial space sector, which until now has seen human spaceflight as the exclusive domain of government agencies. Zhang Xiaomin, chairman of AZ Space, made the announcement to Chinese media last week, setting a timeline that would make his company the first private Chinese entity to send humans to orbit. While China's government-run human spaceflight program has successfully operated the Tiangong space station using Shenzhou spacecraft launched on Long March rockets, this would mark the first time a commercial company attempts such a mission. Founded just 5 years ago in 2019, AZ Space has focused its business on spacecraft manufacturing and space tourism. The relatively young company has secured backing from several venture capital firms, though specific funding details for their ambitious human spaceflight program weren't disclosed. This leaves questions about how the company will finance such a technically challenging and expensive endeavor. The path to crewed spaceflight involves several intermediate steps, which AZ Space has already begun. The company has more immediate plans for 2025, including launches of their self-developed B300 spacecraft and the more advanced Deer 5 spacecraft. These missions are scheduled for July and September this year, respectively, with Zhang explaining that these spacecraft will conduct critical on-orbit docking verification and re-entry tests. This follows AZ Space's December 2023 launch of their Deer 1 spacecraft aboard an iSpace Hyperbola 1 rocket. The company is also developing the larger C-2000 spacecraft with a 2,000 kilograms payload capacity, which they see as a stepping stone toward their ultimate goal of human-rated spacecraft. While the timeline appears highly ambitious by global spaceflight standards, the announcement comes in the context of strong governmental support for China's commercial space sector. The central government has designated commercial space as a key emerging industry to be supported and promoted, with local and provincial governments actively working to attract space companies and foster innovation ecosystems. What remains unclear is whether AZ Space will have access to state-owned technology for their reusable and crewed spacecraft plans, or if they'll need to develop these critical systems independently. Either way, this announcement signals that China's commercial space race is accelerating to new heights. China's approach to commercial space has evolved dramatically over the past decade. When the government first began opening the sector to private capital in late 2014, the initial focus was quite narrow, primarily small launch vehicles and satellites. This marked a significant shift from the exclusively state-run space program that had defined China's approach for decades. In the years that followed, we've seen a remarkable expansion in both the scope and ambition of China's commercial space ventures. What began with modest rockets and small satellites has progressively grown to encompass ever larger liquid propellant launchers with potential reusability, diverse space systems and applications, remote sensing and communications constellations, and more recently, low-cost reusable cargo spacecraft designed to service the Tiangong space station. The emergence of two planned, low Earth orbit mega constellations has provided a crucial market opportunity for these commercial launch companies to establish themselves and build sustainable business models. Much like we've seen with SpaceX in the United States, these large satellite deployments create the consistent launch demand needed to justify investment in rocket development. With AZS Space now setting its sights on crewed orbital spaceflight, we're witnessing what appears to be the beginning of a new phase in China's commercial space evolution. This represents a fundamental shift where private firms may soon undertake human spaceflight activities that have traditionally been the exclusive domain of China's state-run human spaceflight agency. This transformation is occurring with explicit government encouragement. China's central government has formally designated commercial space as a key emerging industry deserving of support and promotion. This top-down endorsement cascades through various levels of government, with local and provincial authorities actively competing to attract commercial space companies to their regions through incentives and infrastructure development. The strategy appears designed to foster innovation ecosystems around space technology while maintaining strategic oversight of the sector's development. It creates a hybrid model where private capital and entrepreneurial energy can accelerate technological progress and commercial applications, while the government maintains involvement in critical aspects of space development. As this landscape continues to evolve, the boundaries between commercial and state space activities in China may become increasingly fluid, potentially creating new models for how public and private sectors collaborate in space exploration and utilization. In a fascinating discovery that highlights the diversity of worlds beyond our solar system, astronomers have recently identified two exoplanets orbiting a star called TOI 1453, located approximately 250 light-years away in the Draco constellation. These newly found worlds represent planetary types that are actually quite common throughout our galaxy, but completely absent from our own solar system. The Discovery team used NASA's Transiting Exoplanet Survey Satellite, or TESS, along with the Harpson high-resolution spectrograph to confirm these distant worlds. What makes this finding particularly exciting is the nature of the planets themselves. One is classified as a super-Earth, while the other is what astronomers call a sub-Neptune. While both planets are intriguing, it's the sub-Neptune, designated TOI 1453c, that has astronomers truly puzzled. This world is approximately 2.2 times the size of Earth, which isn't unusual for its type. However, what's extraordinary is its mass, measuring just 2.9 times that of Earth. This creates an extremely low density that has left scientists scratching their heads about what this planet could possibly be made of. To put this in perspective, this makes TOI 1453c one of the least dense sub-Neptunes ever discovered. The planet's lightweight nature suggests one of two fascinating possibilities. Either it has an unusually thick hydrogen-rich atmosphere extending far above its surface, or perhaps its composition is dominated by water rather than rock. The combination of precise size and mass measurements allowed researchers to calculate the planet's density with confidence, which is what revealed this peculiar characteristic. As astrophysicist Manu Stahlport, who worked on the study, explained, The two planets present an interesting contrast in their characteristics. While TOI 1453b appears to be a fairly typical rocky super-Earth orbiting close to its star with a 4.3-day cycle, TOI 1453c defies easy categorization. This puzzling world raises fundamental questions about planetary formation and evolution. How could a planet grow to such a size while maintaining such low density? What processes shaped its development? And what might its surface or atmosphere be like? These mysteries make TOI 1453c an exceptionally promising target for future atmospheric studies. The research team employed a two-pronged approach to characterize these distant worlds. The transit method using test data revealed each planet's size and orbital period by measuring the slight dimming of starlight as they passed in front of their host star. Meanwhile, the radial velocity measurements from HARPS-N detected the subtle gravitational wobble each planet induces on the star, allowing scientists to determine their masses. What's particularly fascinating about this system is that the two planets orbit in a configuration close to what astronomers call a 3-2 resonance. This means that for every 3 complete orbits of the inner planet, the outer planet completes almost exactly 2. Such orbital resonances aren't random. They're considered a natural consequence of orbital migration, providing important clues about how these planets moved and eventually settled into their current positions. TOI 1453c's extraordinarily low density presents an exciting scientific puzzle. For a planet its size to be so lightweight, it must have a fundamentally different composition than the rocky worlds we're familiar with. The evidence points to either a substantial, hydrogen-rich atmosphere that significantly increases the planet's diameter without adding much mass, or perhaps an interior largely composed of water rather than denser materials like rock and metal. This makes TOI 1453c an ideal candidate for future atmospheric studies using next-generation instruments like the James Webb Space Telescope. JWST's advanced capabilities could potentially analyze the planet's atmosphere, determining whether it's primarily hydrogen or water-dominated, which would revolutionize our understanding of this enigmatic world. The orbital resonance also suggests these planets have remained dynamically stable for a long time, providing a window into the system's formation history. Such configurations typically develop when planets migrate inward through their star's protoplanetary disk, gradually locking into these synchronized orbits. If TOI 1453c does indeed have a substantial water component, it would represent a fascinating planetary category, neither truly rocky like Earth nor gaseous like Neptune, but something in between that we don't see in our solar system. Understanding such worlds could fundamentally reshape theories about how planets form and what kinds of habitable environments might exist throughout the galaxy. And in another exciting discovery, scientists may have finally solved a decades-old cosmic mystery that has puzzled astronomers since 1980. Strange X-ray emissions detected from the center of the Helix Nebula might actually be evidence of a planet being violently ripped apart and devoured by the dying star at its core. The Helix Nebula represents the final stage of a dying star that has shed its outer layers, leaving behind a small, dense remnant called a white dwarf. What makes this particular white dwarf, designated WD 2226, 210, unusual is that it shouldn't be producing the powerful X-rays that telescopes have consistently detected for over 40 years. Thanks to observations from NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton, researchers believe they've finally cracked this cosmic case. The data reveals a Neptune-sized planet orbiting perilously close to the white dwarf, completing a revolution in less than 3 days. Even more intriguing, evidence suggests there may have been a Jupiter-like planet orbiting even closer that met a catastrophic fate. Lead author Sandino Estrada Dorado from the National Autonomous University of Mexico explains, "We think this X-ray signal could be from planetary debris pulled onto the white dwarf, as the death knell from a planet that was destroyed by the white dwarf in the Helix Nebula. We might have finally found the cause of a mystery that's lasted over 40 years. The doomed planet likely began its life at a safe distance from its star. But as the star aged and transformed into a white dwarf, the planet's orbit may have been disturbed by gravitational interactions with other planets in the system. This migration brought it fatally close to the white dwarf, where intense gravitational forces began to tear it apart. What astronomers are witnessing now appears to be the aftermath of this cosmic destruction. As debris from the shattered planet falls onto the white dwarf's surface, it becomes superheated to millions of degrees, producing the telltale X-ray signature that astronomers have been detecting for decades. If confirmed, this would represent the first documented case of a planet being destroyed by the central star in a planetary nebula. The observation offers a sobering glimpse into the potential fate that awaits planets orbiting aging stars, perhaps even our own solar system in the distant future. This discovery provides crucial insights into the fate of planetary systems as their stars reach the end of their lives. What we're witnessing at the Helix Nebula may be a preview of what awaits countless other star systems, including possibly our own solar system billions of years in the future. The research team analyzed X-ray data collected over multiple observations spanning a decade and found something remarkable. The signal has remained relatively consistent in brightness since the early 1990s. This stability suggests we're observing an ongoing process rather than a one-time catastrophic event. But within this consistent signal, astronomers detected subtle fluctuations that repeat every 2.9 hours, providing compelling evidence for planetary remains orbiting exceptionally close to the white dwarf. Martin Guerrero from the Institute of Astrophysics of Andalusia explains, "The mysterious signal we've been seeing could be caused by the debris from the shattered planet falling onto the white dwarf's surface and being heated to glow in X-rays. This steady stream of material creates a consistent energy signature that telescopes can detect across vast distances." The research team considered alternative explanations, including whether a low-mass star rather than a planet might have been destroyed. However, such stars are significantly more massive than Jupiter-sized planets, making them much less likely to be torn apart by the white dwarf's gravity. Interestingly, WD-2226, 210 shares X-ray behavior similarities with two other white dwarfs that are not inside planetary nebulas. One appears to be pulling material from a planet in a more gradual fashion without complete destruction, while another is likely accreting material from what remains of a destroyed planet. These three white dwarfs may represent a newly recognized class of variable objects that offers a window into different stages of planetary destruction. It's important to find more of these systems because they can teach us about the survival or destruction of planets around stars like the Sun as they enter old age, notes co-author Jesus Tawala. By studying these systems, astronomers gain valuable insights into the long-term fate of our own solar system. When our sun eventually exhausts its nuclear fuel billions of years from now, it will expand into a red giant before shedding its outer layers and becoming a white dwarf. During this tumultuous transition, the inner planets will likely be engulfed, while the orbits of surviving outer planets may become destabilized. What we're witnessing in the Helix Nebula could be a preview of Earth's ultimate fate, offering both a sobering reminder of cosmic mortality and a fascinating glimpse into the life cycle of planetary systems. And one more discovery for good measure. For over a century, astronomers have been captivated by the majestic spiral arms that wind through galaxies like our own Milky Way. But recent observations using the unprecedented resolution of the Hubble and James Webb Space Telescopes have revealed something even more fascinating. These grand spiral structures aren't just simple arms, but are decorated with intricate features astronomers call feathers. These feathery structures extend just a few thousand light years, relatively small by galactic standards, but they play an outsized role in galactic evolution. Unlike the broader spiral arms they branch from, these feathers are extraordinarily dense regions packed with gas and dust. They serve as cosmic nurseries where much of a galaxy's star formation takes place, hosting young star clusters and massive clouds of neutral hydrogen where new stars are born. Initially, astronomers believed these feathers were exclusive to the largest grand design spiral galaxies. However, mounting evidence suggests they're nearly universal features, with our own Milky Way sporting these delicate structures as well. What has puzzled scientists for years is how these complex features form. The leading theories have involved elaborate mechanisms, perhaps powerful supernova explosions, sculpting the gas within spiral arms, or vast magnetic fields twisting and compressing matter into these filamentary patterns. The complexity of feathers seem to demand equally complex formation processes. But sometimes the most elegant explanation is also the simplest. In research recently accepted for publication in Astronomy and Astrophysics, a team of astronomers proposed a surprisingly straightforward mechanism. Gravity alone might create these feathers. To test this hypothesis, the researchers designed an elegantly simple computer simulation. They created a basic model of a rotating disk of gas. No stars, no complex physics, just gas moving under the influence of its own gravity. When they ran the simulation, something remarkable happened. The gas naturally fragmented into a series of nested filaments that bore a striking resemblance to the feathers observed in real galaxies. The key insight is that these gas disks are inherently unstable. Even tiny initial clumps tend to collapse under their own gravity, and when combined with the rotation of the disk, these collapsing regions naturally form elongated structures, the feathers we observe in spiral galaxies. When researchers compared the simulated feathers with actual observations, they found broad agreement in size, shape, and density. This doesn't mean the mystery is completely solved. The simulated galaxies were deliberately simplified, lacking many elements we know exist in real galaxies. The next step is to introduce more realistic physics. Those supernovas and magnetic fields do exist and certainly influence galactic evolution. The question is whether they would disrupt these gravitationally formed feathers or perhaps enhance them. What makes this finding so compelling is that it demonstrates how nature can use basic physical principles to generate remarkably complex structures, even at the vast scales of galaxies. Sometimes the universe's most intricate patterns emerge from its simplest rules. The team's simulations were remarkably simplistic by design. Rather than creating a complex model incorporating all the known physics of galaxies, they stripped everything back to the most basic elements, just a disk of gas rotating and evolving under its own gravitational influence. No stars, no explosive stellar feedback, no magnetic fields, just gravity. When they set this simplified system in motion, the results were striking. The rotating gas disk didn't remain smooth and uniform. Instead, it naturally began to fragment, breaking down into a series of nested, elongated filaments that closely resembled the feathery structures astronomers observe in real galaxies. This fragmentation occurs because gaseous disks are inherently gravitationally unstable. Any slight density fluctuation, no matter how small initially, tends to attract more matter to itself. As these regions grow denser, they collapse faster, creating a self-reinforcing process. The rotation of the disk then stretches these collapsing regions into the filamentary patterns we recognize as feathers. What's particularly impressive is how well these simulated structures matched actual observations. When the researchers compared their computer-generated feathers with those seen in real spiral galaxies, they found significant similarities in key properties like size, shape, and density distributions. This doesn't mean we've solved the entire puzzle. The researchers acknowledge that real galaxies are far more complex environments. The next challenge is determining whether introducing more realistic elements, like stellar feedback from supernovas or the influence of magnetic fields, would disrupt these gravitationally formed feathers, or perhaps work in concert with gravity to shape them further. The finding highlights a principle that appears repeatedly across cosmic scales. That immense complexity often emerges from relatively simple underlying physics. From the intricate patterns of snowflakes forming from simple water molecules to the vast filamentary cosmic web stretching across the universe, nature frequently uses basic rules to create stunning complexity. In the case of galactic feathers, it seems that gravity alone might be sufficient to establish the foundation of these structures. It's a powerful reminder that sometimes the most elegant explanations in science are also the simplest. And that brings us to the end of today's episode of Astronomy Daily. From the evolving mystery of dark energy to Boeing's Starliner troubles, China's ambitious space plans, puzzling exoplanets, a star devouring its own planet, and the simple gravitational forces behind complex galactic structures, we've covered quite the cosmic journey together. I'm Anna, and it's been my pleasure guiding you through these fascinating developments in astronomy and space exploration. The universe continues to surprise us, whether it's throwing curveballs at our understanding of fundamental forces or revealing the elegant simplicity behind seemingly complex cosmic patterns. If you enjoyed today's show, please visit our website at astronomydaily.io, where you can sign up for our free daily newsletter. Catch up on all the latest space and astronomy news with our constantly updating newsfeed, and listen to all our back episodes. You can also find us on social media. Just search for Astro Daily Pod on Facebook, X, YouTube Music, TikTok, and Instagram. We love hearing from fellow space enthusiasts, so don't hesitate to reach out and share your thoughts. Until next time, keep looking up and stay curious about the wonders of our universe. This has been Astronomy Daily, and I'm Anna signing off.